Hi, Margaret. This one's kind of short, but I just wanted to go through the order of how we teach equilibrium. You might be a little bit further than this, but I just thought it would be a good review. So when you calculate an equilibrium constant, it could have a big, big value or a small, small value. Here's a couple of examples. So if you have an equilibrium constant which is much bigger than 1, you say that it's product favored. So look at this one. NO2 and O2 over NO and O3 have a Kc, or equilibrium constant, of 6 times 10 to the 34th, obviously an absolutely huge number. When you see an extremely large value, it means that when the equilibrium condition is reached, the product molecule concentrations are way bigger than the reactants. This number is so big, you could say that this is practically zero reactant. Not exactly zero, but practically zero. A chemist would say that this reaction has gone to completion. When you were doing Chem 103, you would assume a reaction went to completion in order to do stoichiometry problems. There are some equilibrium constants that are less than 1. That's when the reaction is reactant favored. This one between oxygen and ozone has a Kc which is 2.5 times 10 to the minus 29. That's ridiculously small. That's a decimal and 28 zeros, then a 2. So there's hardly any of the ozone molecules, but there are a few. Something called the reaction quotient looks exactly like the K expression, but it is sort of, I call it, a snapshot of the reaction before it reaches equilibrium. There are two uses for a reaction quotient. First, it could tell you if the mixture you have is at equilibrium or not. And then second, it can tell you what changes will occur in order for the system to reach equilibrium. If you calculate a Q value and it's less than K, the reaction is going to shift to the right to make more product molecules and consume some of the reactants. If the Q value, the reaction quotient, is greater than K, the reaction will shift to the left to make more reactant molecules and fewer products. I remember my high school teacher drawing this like a number line, so that if the Q value was less than K, the reaction will shift to the right. More products. If the Q value is greater than K, you will make more reactants. You'll see more examples of this as we go along, but let's do something with some numbers. To illustrate this, let's look at this equilibrium between a molecule called butane. So you were doing some organic chemistry. This is a straight chain alkane. And then you have a branch chain alkane called isobutane. Well, at 298 K, remember that equilibrium constants are only true at certain temperatures. At 298 K, the Kc is 2.50. So isobutane is 2.5 over 1, if you're going to think of it that way. Now suppose you had a mixture of butane and isobutane, and these were the numbers that you were given. What is the Q, and then could you predict what will happen? Well, this is pretty straightforward. The Q is just simply the product molecules over the reactants. Both of these molecules have 1s in front of them, so you don't have to do any squareds or cubes. But so we're just going to take the product, 0.0040 divided by 0.0030, and I get 1.3. Now since 1.3 is less than 2.50, the reaction will shift to the right, and it will make more products. It will make more isobutane and consume the butane. Consume butane and produce more isobutane. This will happen until the two numbers are equal. So you're going to keep increasing the product and decreasing the reactant until you get to 2.5. Finally, let's look at this example. Suppose that I have two NO2s in equilibrium with one N2O4. At 298 degrees, the Kc is 170, so this is a product-favored reaction. Suppose that the NO2 in a certain mixture is 0.015 and the N2O4 is 0.025. Is this mixture at equilibrium? If not, what will happen? Well, first find the reaction quotient. So I need to find the product number, 0.025 raised to the first, divided by the reactant, 0.015 raised to the second power. Put that in your calculator, you get 110. Now, similar to the last one, since 110 is less than 170, the reaction will shift to the right and create more N2O4 and consume NO2. Now here's your turn. For the butane-isobutane reaction from earlier, the Kc was 2.50. Calculate these two mixtures in order to find out, are these at equilibrium? And if not, how will they shift? All right. I don't know if I'll have time to make another video today, but I hope you have a great day. Bye.